Hi there. Today we'll be covering the kinetics, so 3.1.5 part of AQA A-level chemistry course. This is typically taught in AS, but it's very important. There are a lot of key concepts here that need to be developed upon for Arrhenius and the other rate equations part of A-level chemistry. So starting off with collision theory, the most important thing to understand with this topic and with this content is that you have particles in a set volume, and when they collide, that not every collision is successful in a reaction, but if you collide and it has a certain amount of energy, that amount of energy will define a successful reaction. We know that as activation energy, and if the particles collide with that activation energy or more, it's a successful collision, so it'll lead to a reaction. On the right hand side, I've got the Maxwell Boltzmann distribution, and this models the number of particles against the particle energy, so it tells us what our distribution of particles are relative to their energies in this kind of set system that we have. So collision theory is linking the energy of a particle directly to its rate of reaction, and the energy of the particle is affected by things like temperature, pressure, concentration, presence of a catalyst, so things that are impacting the system that we're looking at. I've got a few self-test questions again here, so pause me now, have a go at them, and we'll cover them in a sec. Okay, so why do most collisions between particles not result in a chemical reaction? Well, this goes back to our knowledge of the collision theory and saying that actually most collisions, particles, like a particle here for example, does not have sufficient energy to undergo a reaction when they collide. And if we look at the Maxwell Boltzmann graph here, the most probable and the mean energies have been labelled here with these two little points. But which one is which? Well, at the biggest peak, this is where the most particles are present, and therefore we know that this would make sense to be the most probable energy. And therefore this other one here has to be the mean energy. Now notice how the mean energy and the most probable energy are not the same, and that's another key concept to understand. Let's have a little look at the effects of temperature, concentration and pressure on the reaction rate. So using this model of collision theory, we can say that an increased temperature results in an increased rate of reaction. Now, well, why is that? When we increase the temperature, we're effectively increasing the individual energy of each particle. So the mean number of particles with sufficient energy will increase. I've drawn this here as a little model of the Maxwell Boltzmann curves. It's important to understand as well, like you should be able to draw things like this to explain it. If we look at this here, and this is the sufficient energy barrier, or the activation energy, which we could label as EA, or we can label as AE. Anything above this line, on the right hand side, has enough energy. And so we can see here that the area under the curve here is less than the area under the curve here. And because this curve, because it's a curve and not a straight line, a small increase in temperature can have a massive drastic change in how many particles have sufficient energy, and therefore just how quick the rate of reaction actually is. So looking at increased concentration pressure, we have a similar sort of situation, but the way that it affects it is different. When we're looking at temperature, it is that the energy of individual particles is increasing, whereas when we're looking at concentration and pressure, we're looking at the actual confinement changing. So with concentration increase, we obviously have more particles per set volume, as I've kind of drawn here. And we can see that therefore we're going to get more collisions because the space hasn't changed, but it's more crowded. Those more collisions result in an increased rate of reaction. The most important thing to understand here is that the greater the collision frequency, the increased rate of reaction. And that's the correlation that you need to be able to understand and explain for this course. Now, a pressure increase, I like to view it as a way of confining the system further. So you're squashing that square down, and therefore the collisions are again going to be more frequent, giving us that increased rate of reaction. Looking at catalysts, it's a little bit different. Now, the definition of a catalyst is a substance that increases a rate of chemical reaction by providing an alternate reaction pathway. The important thing to note here is that catalysts are never used up in a reaction. They are not changed in state or phase or anything. I've drawn here another Maxwell Boltzmann distribution. Now we've got a standard activation energy, which, as we've seen before, anything on the right hand side here, this is sufficient energy to react. But this mark here defines our new activation energy, and that is with a catalyst. And this is how we can physically demonstrate the effect of a catalyst on the Maxwell Boltzmann curve. We simply have the activation energy go more to the left-hand side. So that's the lower alternate reaction pathway, and that's meaning that our overall, we've gained this amount of area, and therefore we are seeing more particles with sufficient energy in order to react. So let's have a go at a past paper question. Hydrogen peroxide solution decomposes slowly to form water and oxygen, and the reaction is much faster in the presence of a manganese oxide catalyst. So they've given us some data, and the important thing is, if they're ever giving you information such as this qualitative information about what the catalyst is in form, most likely you're going to be answering a question about activation energy or about surface area. The graph shows how the volume of oxygen collected varied with time in experiment 1. So this graph purely just shows experiment 1. And it says, explains in general terms how a catalyst increases the rate of reaction. Well, going back to this and our little model here, we know that so it offers a different pathway, and that different pathway has a lower activation energy. So usually you'd flesh it out a bit more, but I'm just writing the basic points to communicate that. So different pathway and lower activation energy. Now, looking at the next point, draw two lines on the graph to show how the volume of oxygen collected varied with time in 2 and 3. Now, let's have a look. If we're drawing them on the same graph, it's important that they're relative to each other. So 1, we've got 1 mole of hydrogen peroxide, same amount of volume, the same temperature. Now, in experiment 2, the only thing that has changed is that we've got powdered catalyst instead of lumps. Now, what difference does that actually make? If we have powder, we've got very fine particles, such as this. So this could be powders. And if we've got lumps, we've got large chunks. Now, they're both the same catalyst. What is the difference here? It's surface area. This has an increased surface area, this has less surface area. Therefore, the one with increased surface area will have more contact with the reactants and will be more able to catalyze the reaction. So we can confidently say that our powder catalyst will be faster. And therefore, it's important that when we draw this curve, we draw it steeper to show the increased rate of reaction. But ultimately, it will taper off at the same level because we've got the same number of moles of concentration and the same temperature. Now, looking at number 3, we've got half the moles and we've got lumps instead of powder. So we can simply draw a steeper curve, but it's got to end, beg your pardon, sorry, a less steep curve, and it's got to end at half the equivalent height. Now, if you ignore my dodgy drawing, you can see here that I've ended it at half the height and it should be less steep. That is because we've got half of the moles of hydrogen peroxide and we don't have any change in that catalyst relative to that first one. So I'll label this as 2 and this as 3. Explain in terms of collision theory the effect of increasing the concentration of hydrogen peroxide on the rate of reaction. Now, looking back at what we know here to be the difference in concentration and pressure, or when it changes the system, we know that more particles per same volume is what we get when we increase the concentration. So more particles per same volume, or set volume, or molecules. There's a lot of ways you can write this, but the main concept stays the same. And what does that mean in terms of collision theory? Well, when we talk about collision theory, we're always talking about the number of successful collisions, and we know that the number of successful collisions will increase. And that is simply because we have more collisions to begin with, because we have more particles per that set volume. Going back to the first note, the most important thing with this topic, just simply to understand, is the effect that this notion of like particles and collision and successful collisions, that's the most important thing to grasp in collision theory, is that not all collisions result in a reaction. It is dependent on the energy.